Okay, let's go ahead and do this example today. It's another example of root locus design. Root locus design, we remember, it basically has two equations, and so we can solve for two unknowns. And so the two equations we're going to exercise again today are the angle criterion and the magnitude criterion. Okay, all the basic problems that we can deal with basically come down to these two equations, angle criterion and the magnitude criterion. And we're going to try to design a compensator today for a system that uses a proportional plus integral controller. And so the application, yes? Yes. Okay, so the angle criterion and the magnitude criterion we've been covering. We did last week as well, did some examples. So there's nothing new this week. There's no new materials. The test is on Friday. And so these are just more examples, all right? So what I recommend you do is not try to memorize how we did this particular example, because if I change the problem a little bit, then you'll feel lost. But basically it boils down to understanding how to apply the angle criterion and the magnitude criterion. Okay, so here's the application. We'll do an application today where we're trying to do a speed control system. So we can get that thing to focus this morning. And so we have, for example, maybe a motor here that we're trying to control the speed. And we apply a voltage to the motor. And then we measure the speed and we compare it to the desired speed. And then what we want to do is design some sort of controller here. Now let's take a look at the process model. If we put in, for example, a step response, it might look like this, a step input. Let's put in a step voltage in time, then the speed might do something like this. Okay, so this would be speed as a function of time. Okay. We might model this as a first order, okay, a first order response between voltage and speed. Okay. So let's just choose a model for our example today. Let's suppose the model is 10 over s plus 2. Okay, this is our transfer function for this part. Okay. Now, so what we have then is, if we take a look at the model now, and redraw and insert this, we have 10 over s plus 2. And then we want to put in some sort of compensator here so that we get the desired response in the system. So here's speed, and here's the desired speed. Okay. One of the things that we typically want in a speed controller is we want the error to be small. Okay. So for steady state error to be 0, let's see, this is a desired characteristic. If we want steady state error to be 0, then the open loop must be type 1. Okay, in other words, here's G of S, our process. CG of S must have a pole at S equal to 0. A pole at S equal to 0 makes it type 1. Okay. Right now, we don't have that. We have a pole at -2. So that means we have to insert that pole with a compensator. Okay. So the first thing we might try is we'll just let the compensator be an integrator then. Okay. Okay. Then what that gives us is that CG of S is equal to 1 over S plus 2. So let's sketch the root locus diagram and see what this looks like. Okay, I'm going to put in a K up here so we can adjust the gain. So we have the plant pole here on the real axis. I'm sorry, the plant pole is here on the real axis at -2, and this is the compensator pole, like so. And so the root locus will look something like this. We'll do the real part first, the real axis part first. Okay. We have 2 branches because we have 2 poles. The branches start at the x marks and go to the finite zeros. There are no zeros. So that means they have to go off the page. And we can calculate the asymptotes. There are 2 asymptotes because there are 2 poles. And that means we have to put in a vertical line like this somewhere on our picture. And the vertical lines will be vertical, like going up and down like this. This angle here is 90 degrees. And this point here, the centroid, is going to be the sum of the poles, which is 0 minus 2 minus the zeros. There are no zeros. There are no zeros, so there's nothing to remove. And then divide by the number of asymptotes, so it's 2. So the answer is equal to -1. So this point here should be at -1, which means I need to put my dashed lines right here. Okay. And so the completed root locus will look something like this. Okay. So now let's suppose we desire a settling time TS equal to 1 time unit. Okay. And we want overshoot less than 5%. Okay, so here's our time specification. Notice everything so far has been in time domain specifications. Earlier we said the error needs to be 0. Okay, we want error to be 0. We could calculate the error function, and we discovered that we basically need a type 1 system. In other words, we need DC gain equal to infinity, which is why we introduced the pole at S equal to 0. So we said the way we can introduce the pole at S equal to 0 is put in a 1 over S in our compensator. And that changes this to a second order problem. And now this describes the roots. Now we desire the settling time to be, again, this specification. This is a time domain specification. Okay, so it means the sketch, see, will look something like this. Okay, not much overshoot. If we put in a 1 for a step input, then we would expect the output to settle at 1, and we want the settling time to be equal to 1. Okay. Now, these two things basically tell us that if T of S is equal to 1, then the time constant has to be equal to, say, 1/4. And if we want overshoot to be small, that means the complex and imaginary parts of the roots should be equal. The real part of the desired poles has to be equal to the imaginary part of the desired poles. That's a starting point. Okay. So let's draw this picture again and see where we should have the poles. So let's draw the root locus diagram again. We have the plant poles here. We added a compensator to make the steady state error equal to 0. But we want the time constant to be equal to 1/4, which means it needs to be on a line somewhere out here at -4. And we want the real and imaginary part to be the same, so this is where our closed loop pole should be. So if you're using SISO tool, this is where our pink box needs to be. S star is equal to -4 plus J4. Okay. But our root locus right now is doing this. And so what we discover is that our root locus does not go through this point. It doesn't work, because the root locus is here and we want it to go through there. So we need to do something to kind of like bend this around. Okay, we need to do something that makes the root locus bend more to the left. Okay, so this is why we might consider a PI controller. So let's think about the PI controller. Instead of just having integral control, let's consider a PI control. A PI controller will say that C of S is equal to, you could have two terms, a proportional plus integral. Typically we do it like this, KP, that's a proportional term, plus, one way to do it is KI divided by S. This is the integral term. Okay, proportional plus integral. This term we looked at already. We said let's add the integrator that raises system type, but let's try to make the system respond more quickly by adding a proportional term here. Okay, let me get common denominators and add these two terms together. So that means I have KPS plus KI divided by S. And if we take a look at this system, basically what we say is that we have a pole at S equal to 0, and then here we have a 0 at S equal to negative KI over KP. So in the complex plane, this is the real and imaginary axis. In the complex plane, this is the compensator. This is the compensators in the S-plane. I've not put on here the process. I'm only sketching the pole and 0 of the compensator. So this is at the point negative Ki divided by Kp. Okay, let's see what would happen if we add the Pi compensator to the root locus diagram. Okay. We're going to add the Pi compensator to the root locus. So let's see if this would help. This is the real and imaginary axis. Here's the plant, -2. This is G of S. And we're going to add a compensator. The compensator is going to add this and this. Okay, so these two parts come from C of S. Okay, now let's take a look at the root locus diagram. easy. One of the rules is let's take care of the real axis. See where on the real axis there could be closed loop poles. And we'll see that there could be some here and could be some here. Okay. We have two branches because we have two poles. We have two loci. They have to start here and end here or go off the page. Okay, so we have two poles, 1, 0. So the difference between that is the relative degree. That means we have one asymptote. And it has to go look like this. And so it's got to go on the real axis, so that means the asymptote's going like this. Okay, so we have two branches. They start here and here. They start on the X marks. They move around symmetrically, and they somehow have to end up over here and here. So this is probably what the root locus will look like. Okay. So as K increases, the closed loop poles move this way, and then the closed loop poles move like this, and then the closed loop poles move like that. And the question is, could this pink box, I might get lucky, there's actually a pink marker here. Could that pink box be on the root locus diagram? And so that point should be -4 plus J4 if we design this correctly. Okay? So this is the unknown. We don't know where this is. We need to adjust this and adjust the gain. Okay? So we need to design the 0 location and the gain. Okay. So there's two unknowns, but we have two equations. Okay. All right. Let's redraw our system and draw it this way in a way that's easier to do root locus design. This is now our problem. So after all this discussion, we've come down to now finally getting to a compensator that we think will work, but we have two unknowns. So this is our problem. What are K and Z? We have a 0 and a pole. Now I've written this in a slightly different form than the way the PI controller was originally written. I originally wrote this is the same thing. This is equivalent to KP plus KI over S. Just do a little bit of algebra to get it into this form. But this form makes it a little bit easier for us to design in the root locus. And what we want is we desire a closed loop pole at S star equal to -4 plus J4. Real axis, imaginary axis. Here's the plant pole at -2. We're going to add in a compensator pole at the a pole at the origin. And then somewhere out here there's going to be a compensator 0. This is -Z. And we want -4 plus J4 right here. And we want the root locus to pass through that point. Okay, so the first thing we'll do is let's do the angle criterion. I'm going to call this theta 1, call this theta 2, and call this theta Z. We we do the angle criterion first. Okay. Try the angle criterion first. So if we're doing it by geometry, what we're saying is that theta z minus theta 1 plus theta 2 has to equal to 180 degrees. That's the geometry we have to work out. This is unknown, but we should be able to figure out what theta 1 and theta 2 are. Okay. Now, if we're doing it on the calculator, not by geometry, well, either way, you need your calculator. Angle criterion says the angle of CG of S evaluated at S star has to be equal to 180 degrees. That means the angle of S plus Z, S star plus Z, S star plus 2, this angle has to be equal to 180 degrees. S star is equal to negative 4 plus J4. Okay. So the angle of negative 4 plus J4 plus Z minus the angle of negative 4 plus J4 plus the angle of 2 plus negative 2 plus J4 has to be equal to 180 degrees. Okay, so plug in these into your calculator. So this is the unknown angle, theta z. This is 135 degrees. And this I need help with. Negative 2 plus J4. I need help with this angle, theta 2. Anybody got it? Okay. Somebody said 116.6. Do we have a second on that? Got a second? Okay, somebody agrees. That's 180 degrees. Okay, so just look at all these signs floating around, all these different places where one could make an algebra error. And that's the most common thing that goes wrong on the test, is that we make an algebra error. It looks kind of reasonable. If this is 135, this should be an angle that's smaller than 135. So that's another sanity check. Yeah, that's a number smaller than the 135. That looks reasonable. Okay, so theta z is equal to 180 degrees plus 135 plus 116.6. So what do we get for that? I get 431.6. Is that right? Okay. 431.6. So what's 431.6 degrees from this point? I'm measuring from this relative to the real line. So 431, I got to go all the way around. I got to go 360 and then continue going. Okay? So what we should do to get this reasonable is to subtract 360 degrees. That doesn't change the problem. It's the same angle. If I subtract out 360, I get 71.6. Okay. So now we have this, and according to our solution, this should be 71.6. So now we have this little bit of a problem we have to deal with now. Negative 4 plus J4 here's the 0 at negative z. This point here is at negative 4. This is the real axis. I'm not going to draw the imaginary axis. This angle is 71.6 degrees. Okay, so we need to remind ourselves what is the trigonometry, geometry, pieces of math that we need to be able to find z. Okay? This height, I know this height. This height is 4 because it's J4. This is a distance of 4. I should be able to find out what this distance is here. Call it x. So 4 over x is equal to the tangent of 71.6 degrees. So this distance x is 1.33. Probably we didn't do any round off. It might turn out to be 4/3. I'll let you check on the calculator to see if it's exactly 4/3. So if that is 1.33, then z is equal to all these minus signs are going to throw us off, right? This is where we can get messed up. .33. Okay. So now our root locus diagram, things are starting to come together. We have the plant pole at -2, a compensator at 0, a pole at the origin. And now we have something out here at -5.33. And the root locus diagram is going to be this and this. And if we've done everything well, then -4 plus J4 and -4 minus J4 should be on the root locus. Okay, because we did that by using the angle criterion. Okay, now we need to find K. That's the next point. The next thing we have to do is find K. And we do that with the magnitude criterion. Okay, so what that tells us is that magnitude criterion says that K is equal to 1 over the magnitude of everything that's known. That's CG of S evaluated at S star. Let me squeeze that over here. K has to be 1 over S star plus 5.33 divided by S star. And then the plant is S plus 2. So we're going to take the magnitude of all that. So draw some lines here. Call this line L1, L2, and call this L3. Oh, I'm sorry, there was a 10 here. There was a 10 in the plant. It's an easy thing to forget. Don't forget the 10 in the plant. I think the original problem had a 10, right? Yep. I've been missing the 10 in a lot of these calculations, but it doesn't matter because up to now, I haven't had to deal with, I haven't had to deal with the magnitude. I haven't had to deal with the magnitude plot. I think every block diagram should have a 10, but this 10 doesn't affect the angle criterion. So fortunately, that's not a problem. But it does affect it in the magnitude. Okay, so what that gives us, back to the magnitude criterion, S star plus 5.33, that's evaluating this length, that's L3. And I have to multiply by 10, because that's the process gain. S star is this length, which I know is 4 times square root 2. That's L1. And then this length, L2, also has to be put in. L2 is square root 20, I think. Because this is negative 4 plus J4. So this is 2, that's 4. 2 squared is 4. 4 squared is 16, square root 20. And L3 requires a little bit of calculator work. Do we have a number? 0.6? Ooh, it's less than 1. Okay. I recommend everybody work through the example. Check to make sure it get the same numbers. Okay, so the bottom line is that we have 2 unknowns, 2 equations. The basic root locus design, basically we have 2 equations. 2 equations. We can solve 2 unknowns. Okay. The 2 equations are angle criterion and the magnitude criterion. Okay. So those are our 2 equations. Always do this one first, and then on this one, when we do the magnitude criteria, remember process gain, as I had forgotten today. Okay, we've done 2 examples. The examples we did last week. We did a phase lead. This was last week. And today we did a ideal phase lag, a PI controller. It's a type of phase lag. In both cases, you have 2 unknowns. You don't know K, and you don't know some parameter of the compensator. But we have 2 equations, so we just set up 2 equations and 2 unknowns. All right. That's a good place for us to stop today. What I'll do on Wednesday is I'll do another example. I'll do an example without any geometry. Because this is 2 equations and 2 unknowns, you can say, well, aren't these just algebra problems? In a sense, they are algebra problems. The way I've got it cast right now, because it involves angles, it looks like it involves trigonometry. But you can set up the problem also. Simple problems can be set up to be done entirely by algebra. And that's what I'll try to show an example on Wednesday.